As we take the pictures, they were mixed. As we take the pictures. So last Monday, we were discussing examples of application of probability to insurance, particularly the effect of deductible and caps. Have you heard of deductible before, Maggie? You took Start With Me 205? When? Online? Oh yeah, that's quick 7-week last semester. Yeah, I remember. Yeah, so no, we didn't discuss deductible there. Deductible is a principle in insurance in which you can set the amount from which you expect your insurance company to compensate you. If you have a loss, for example, you can insure your car with a $500 deductible, meaning that if you get into trouble and it will cost $1,000, the insurance is only going to cover 500. If it is 700, insurance is only going to cover 200. With that, it helps to reduce your premium. The premium is the amount you pay for the insurance. So when there is a deductible D, can you see? When there is a deductible D, you want to determine the random variable of. We want to define the payment amount. If X is the random variable of the amount of loss, and when you get into a car accident, you cannot tell how much the damage will be. Is a random variable. So if X is that amount, then, and the deductible is D, what it means is that if the loss is less than the deductible, you will be paid nothing. The insurance paid you nothing. But if the loss is above deductible, insurance pay you the amount of loss minus the deductible. So that is generally used to determine the expected amount you will receive when you take an insurance. So another aspect is the maximum. Insurance does not cover you indefinitely. It covers you until infinity. Even health insurance, when you take an insurance, there is a cap amount. That is, the insurance can only cover you up to a certain amount. Like most basic insurance, they will say they will pay you for what they call personal injury protection if you are hurt in an accident, and if you destroy something or somebody's car, they will cover it. That's basic insurance required by almost all states. But they set a maximum. Personal injury protection might be 10,000, and other cars could be like 20,000. That is the maximum, which we are calling here a cap. So when there is a cap on your coverage, then the payment amount is the loss amount if it is less than the cap. Or the cap here is C. That is the inconvenience of copy and paste. And here is C. So you can also have both. You can. So this is the payment amount, how it's related to the loss amount. If you have both which are not included, you can figure it out. If you have both deductible, and cap, then if the loss amount is X, the payment amount will be 0. If X is less than Z, will be x minus d if d is less than x less than the cap, and it will be cap minus d if c is less than x less than b. B is like the range for the possible payment. It could be infinity if we assume that it can go to infinity, but we are defining our random variable on a closed or open interval AB. I did not put this one here. It's just a combination of both. Let's do this example. The loss amount x has a density function 1 over 1,000 when x is between 0 and 1,000. That is the density function that the loss amount follows. The insurance policy has a cap amount of 500 per loss. Calculate the expected value of the loss. Calculate the expected amount of the benefit payment. And then calculate the expected amount of the portion of loss not covered by insurance. Here the density function is f of x equal to 1 over 1,000, 0 less than x, less than 1,000, 0 over x. And the cap amount is 500. We have three questions: expected loss, expected payment, and expected. I cannot do this directly, but actually, this is just to keep in mind because I'm going to change the screen. So the expected amount not covered. So we want to recall that the payment amount here is x if 0 is less than x, less than the cap amount, and it is the cap. This is the payment relation to the loss. Now let's start with the first question. Expected loss, the integral from 0 to 1,000. F of x dx, which is 0 to 1,000, x over 1,000. So, which is equal to 1,000 squared over 2,000. It is 1,000. So the expected payment amount for this policy is 500. Do you understand this? That's the expected loss. amount of the loss. Now, what will be the expected payment? It will be integral from 0 to C. C here is 500. The cap is 500. 0 to 500, x over 1000 dx plus integral from 5000 to 1000 c over 1000 dx. So we know here that our c is the cap was 1000 from the problem, which is covered now. And so E of y is equals to this one, 1 over 1000 x squared over 2, 0 to 500. Plus 1 over 1000 which is 500 square over 2000 plus 1000 minus 500 So this C here is 500, which is missing in my computation. This is 500 square. There is some correction I will make here. So follow what I'm doing here. This 500 square over 2 is for this integral divided by 2 times 1,000. And here we have 500 over 1,000, which is this expression here. And here is 1,000 minus 500, which is 500. Multiplying this 500 gives this 500 square. So I can put a square here. Then you have here 1 over 2. So this is 500 square over 1,000. Which is 750 over 2, 350. So with a cap of 500, the expected payment amount is 350. Yes. Oh, sorry. Yeah, that's right. So essentially, it's this integral that we are doing with c equals to 500. So the next question is to find the amount unpaid. What do you think will be the expected amount unpaid? What is the expected amount of loss? What is the expected loss in this problem? Let Z be unpaid amount. Then Z equals to 0 if 0 is less than X, less than 500. If the loss is 500, all the 500 will be paid. 500 and less, the whole amount will be paid, right? So the unpaid amount is 0. And if it is more than 500, the unpaid amount will be, unpaid amount will be what? 500 is less than X, less than 1,000. Do you understand what I'm saying here? If the cap is 500 and the loss amount is X, then if X is less than 500, all the money is paid. So the unpaid amount is 0. If X is bigger than 500, the amount paid will be 500 because the cap is 500. That will be So the unpaid amount is x minus 500. So E of z is equal to 0. The integral from 500 to 1000 x minus 500 divided by 1000. X squared over 2, 500 to 1000 minus 500. Which is 1000 square over 2 minus 500 square over 2 minus 500 square. I'm sorry, here is 2000 for this 1000 which is here. There is a 1000 here. This 1000 which is dividing this factor, I keep forgetting it. So we can say that E of z is equals to this is 2 times 500 square. So there is 500 square all over here, which I would put it here, 500 square over 1000. Here will be 2 square 4 over 2 minus 1 over 2 minus 1. Five hundred square over 2, 500 square over 1000, 25 and this is 3 over 2 minus 1. Which is 1 over 2. Let me just write here 1 over 2. I wanted you to say this before we calculated it, but I want also that you can see how you could calculate it. So we say expected loss is 500, and we say that the expected payment is 375. So naturally, the expected unpaid amount is 125. So this is an example that I want to skip for now, where you have you are given a random variable and you are asked to calculate the expected value of the loss. I'm going to remove this. Nothing is so we have f of x equals to 3 over x for x greater than or equals to 1. This portion of it is not part of. The insurance policy has a cap amount of 500 per loss. I will delete it. I cannot delete it now. This statement was not meant to be there. I copy and paste most of the time and change things in there. So I want to finish this chapter today. So I'm going to skip this example. It is essentially the same thing I've just done. You will change the deductible to 10 and the cap to 10 and do the same thing and see for yourself what difference it makes. So we have done the moment generating function. What I want us to do today is some examples of moment generating function. We did all this last time. So I want us to look at the moment generating function of some specific function that we have learned. I think with 20 minutes, we can do that and complete and do some examples of. Yeah, this theorem is also important. This property of moment generating function. I decided to be typing my note this year because I don't have notes. I want to have some notes. So that's why you couldn't be seeing me struggling with some mistakes there. I type and I teach, and when I'm teaching, I'm reading it over. So we proved this last time, remember? That the moment, the kth moment is the moment, the kth derivative at 0 give us the kth moment. We did this last time. What I want to add here is the moment generating function of a linear transformation, the moment generating function of a sum of independent random variable, and identically distributed random variable. So this theorem is here. So the first property we did last Tuesday, no, it was last week. The moment generating function is used to define moments by taking the k derivative of the moment at 0. The kth moment equals to the kth derivative of the moment generating function at 0. So let x be a random variable with moment generating function mx of t. But y equals to ax plus b. This is a linear transformation of x. What is the moment generating function of y? It's e of ety. By definition, moment generating function is the expected value of the exponential t times the random variable, which is equal to, for Let's write it as E of ET AX plus B, which is E of E ATX plus BT, which is equal to E of ATX times E of BT. Is that right? Using the rule of exponential. Now, this is the expectation of ATX, and that an EBT is like a constant. It doesn't have X. EBT, it does not have X. So we can take it out as EBT and leave in EATX. We can write it as EBT, moment generating function of X, AT. Remember that the moment generating function is what? The moment generating function. If this T is 80, then we have 80 here. So that's the first, that is the second property here. This second property, what I just proved. Let's prove the third property. The third property say that let x1, x2, xn be a sequence independent random variables, and let S be across to the sum of the xi, I from 1 to n. Then what is the moment generating function of S? It will be E of ETS, which is E of E tx1 plus tx2 plus txn. So that means ms of t is equal to E of, because of the multiplicative property of the exponential, etx1, etx2, etxn. I am going to use I'm going to do this for 2, and then you will understand how to generalize it so that it becomes simple in your mind. So let's take 2 random variables. Suppose I want to find E of ETX, ETY, when X and Y are independent random variables. And assume that X and Y are independent and discrete. Then this will be ETX, ETY, E of X, Y. This sum on X, sum on Y, which is sum on X, sum on Y, etx, ety, now px, py. I don't want to shortcut. I don't want to write too much. I would write px of x, py of y. Let's just assume that it's px of x, py of y. The marginal distribution of x and y because x and y are independent. Then if I do the sum, if I want to do this sum for x alone, for y alone, we do the sum on y first, and then all term without y becomes constant. And it will be p of x, etx, sum on y, ety, p of y, which is sum of etx, p of x, and this quantity is the moment generating function of y, which can be taken out. And this one, this is my of t, and this one is mx of t. So what I'm saying here is that I can use the property that if two random variables are independent, then the moment generating function of their sum is the product of their moment generating function. So when we have a finite sum, we can generalize anything we can do for finite sum from 2. We can separate 2. If we go to 3, x plus y plus z, we do x plus y as 1 and then z. If we do 4, 5, we can do 2, and gradually we end up everything. So this shows that ms of t, this one, is equal to mx1 of t times mx2 of t times mxn of t. That means the moment generating function of the sum is the product of the moment generating function. The last one is immediate from here. In the last property, this number 4 says that if the xi are independent with the same distribution, then their moment generating function are the same. And instead of having a product like this, we have that same distribution multiplied by itself n times. So an example, we did this. An example is the moment generating function. We will use that property as we do moment generating functions for binomial and the other distributions. So moment generating function of the Bernoulli distribution. Remember, the Bernoulli distribution is a single trial in which x is the number of success. Probability of success equals to q equals to 1 minus p. And we have a distribution like this, x, p of x, 0, 1, q, and p. So the moment generating function of x will be p of etx, which is equal to, when t equals to 0, etx is a transformation of x by exponential. Etx here will be, when x equals to 0, it will be 1. If x equals to 0, et0 is 1. And when x equals to 1 et, 1 is et. So the moment generating function here will be 1 times q plus et times p. So this is the moment generating function of the Bernoulli distribution. Now observe that every binomial distribution is the finite sum of independent Bernoulli random variables. Now let x and p be a binomial distribution. Then x is equal to the sum of the xi, I from 1 to n, where each xi is a Bernoulli distribution. Xi is, do you remember that? If you are counting the number of success, it's like what is the number of success on the first trial plus the number of success on the second trial, the number of success on the third trial to the n. So each of those trials can be defined as a Bernoulli distribution. And for that reason, the moment generating function will be the moment of the sum of x Bernoulli distribution. So that takes care of the moment generating function of the binomial distribution. So the moment generating function of x is x of t equals to q plus et raised to power n. Because of that proof that if you have a sum of independent identically distributed, that is with the common distribution, then the moment generating function of their sum is the product of their moment generating function. Since they are identical, it's the same thing power n. So we have completed the moment generating function of the Bernoulli distribution, and we know that a random variable is the sum of independent Bernoulli distribution. So this takes care of the moment generating function of the binomial distribution. We are going to do the same thing for geometric and for negative binomial and Poisson on Friday. I thought we will finish today. We'll finish chapter 5 and we will do at least 2 or 3 sections